Soft connective tissue of all body are complex fiber-reinforced composite structures. Their mechanical behavior is strongly influenced by the concentration and structural arrangement of constituents such as collagen and elastin. The mechanical properties of soft tissue depend strongly on the topography, risk factors, ages, species, physical and chemical environmental factors such as temperature, osmotic pressure, pH, and the strain rate. This table presents the range of values of mechanical properties and collagen elastin contents in some representative organs, mainly consisting of soft connective tissues. The skin is the largest single organ. It supports internal organs and protects the body. In a simplified way, we explain here the tensile stress strain behavior for skin, an organ consisting mainly of connective tissue, which is a representative of mechanical behavior of many soft connective tissue. For the connective tissue part of the skin, the three-dimensional network of fibers appears to have preferred direction parallel to the surface. However, in order to prevent out-of-plane shearing, some fiber orientations also have components out of plane. This figure shows a schematic diagram of typical J-shaped stress strain curve for skin. The overall mechanical response of skin tissue under applied tension can be divided into three main phases. Phase 1 illustrates great tension at low load as the dermal fiber oriented towards the load axis, after which the dermal fiber began to uncramp and become progressively more alien, resulting in an increased stiffness. Finally, the fiber come under direct load, culminating in an almost linear third phase.
Tendons are composed of collagen and elastin fibers with a structural hierarchy. In the tendons, the fibrils are composed of many crimped collagen fibers, and these fibrils are adhered together. Tendons are highly responsive to increased mechanical loading and depth through changes of the mechanical, material, and morphological properties. They are also showing the highest tensile strength amongst soft tissue. The structure and composition of tendons allow for their unique mechanical behavior, reflected by a stress-strain curve consisting of three distinct properties. The first section is the toe region. This is where the straightening or uncrimping of crimped tendon fibrils occurs by mechanically loading the tendon up to a certain strain at approximately 2%. The slope of the toe region is known as the nonlinear stress-strain curve. The linear region is the physiological upper limit of tendon strain, in which the collagen fibrils orient themselves in the direction of tensile mechanical load and begin to stretch. If stress is less than 4%, the tendon will return to its original length when unloaded, also known as the elastic region. Therefore, this portion is reversible and the slope of the curve represents the Young's modulus. The yield and failure region. The tendon stretches beyond its physiological limit. Stiffness is reduced and the tendon begins to fail, resulting in irreversible plastic deformation. If the tendon stretches beyond 8 to 10% of its original length, it will begin to undergo microdamage, leading to the eventual macrodamage and failure. Tendons transmit significant forces from the muscle into movement of the bone. Tendons are sensitive to their mechanical environment. Following a period of enhanced mechanical loading, tendon stiffness may increase to maintain physiological ranges of strain during movement, since the ultimate tendon strain is pretty much constant. Two mechanisms could account for an increase of tendon stiffness: A. Increase of Young's modulus, and B. Increase of cross-sectional area. Tendons usually respond to increased mechanical loading within 2 months. Shorter intervention durations, 8 to 12 weeks, may induce tendon adaptive responses. However, longer durations, bigger than 12 weeks, seem to be more efficient, and their effect has been clearly demonstrated in many studies. It was shown that Achilles and patella tendon stiffness did not increase significantly after 2 months, but reached statistical significance at the end of the 3-month training period.